Intuitively, we think of our immediate surroundings as purely three-dimensional space. Everything can be defined on an x, y, and z axis. If I take two objects and I move this book on quantum mechanics right, left, up, down, I could move it anywhere and bring it back to the same position, and our coordinate system would tell us that nothing has changed. But we know that something fundamental has changed: time.
Let's introduce a new coordinate system, four-dimensional spacetime. Condensing the three dimensions of space into one, and using one time axis, we can graph the book situation.
The astrophysics book only moves forwards in time, whereas the quantum mechanics book does deviate in its spatial position, which means it takes a different path through space-time. To be in space is to be in time.
This unification of the concepts of space and time forms a fabric we use to describe the universe. It was with this fabric that Einstein disproved Newton's perception of gravity. So, if Earth orbits a sun, it seems like there's some sort of magical force that keeps it in this state. But what force? Where does this force come from? There's nothing between these two bodies except empty space. Exactly.
Looking at a 2D atlas map, we can draw the shortest path between New York and Moscow as a straight line. But looking at a globe, we know that the shortest distance isn't a straight line at all, but a curve. This is called non-Euclidean geometry, and it proves that the shortest path isn't necessarily a straight line.
This same logic can be applied to the universe. Einstein discovered that there was a curvature in the space-time around bodies with mass, and that gravity was just objects following the shortest trajectory through space-time, a geodesic. This led to his theory of general relativity and the Einstein field equations.
Shortly after Einstein's publishment, Karl Schwarzschild derived the first exact solution to the Einstein equations, the Schwarzschild solution. It's also known as the black hole equation.
When a star dies, it means it's got no hydrogen left to burn. This means that the inwards gravitational pull overcomes the outwards explosive force of the star, causing all the particles to collapse in on themselves. But where does this ever stop?
The star's mass condenses into an area so small, ultimately a volume with a radius of 0, that its density becomes so great that it warps space-time to such a degree that nothing is fast enough to escape, not even light.
But how does this work? Since when can you divide by a radius of 0? Well, we can't, and that's purely because the limit of our theoretical physics stops short. We know that this point exists. It's called a singularity, and the nature of it is one of the deepest mysteries at the bottom of physics.
So now that we have the fundamental understanding of space-time and the fact that singularities exist, enter Edwin Hubble. Now, Hubble proved by observing redshift of distant galaxies that they were moving away from us. He came to the conclusion that the universe was expanding. So if space is expanding as time moves forward, then what happens if we turn back the clock?
We peer back into time, and we see that space is contracting, getting smaller and smaller and smaller until we reach the beginning of space and time itself, where space-time is but a single dimensionless point. Then this point exploded, birthing the entire universe and everything you've ever seen. This is called the Big Bang.